Hi guys, welcome to my channel. In this video we are going to solve the questions about the reinforced concrete, and the question will be analyzing of a double reinforced beam. You can see the cross section now on the screen. So let's solve the question. The first, we are going to make an assumption that the compression steel has yielded. Our assumption is assume that the compression steel has yielded. Due to this assumption, we are going to solve the question. So let's write an equilibrium. Due to this equilibrium, we are going to obtain the neutral axis and also the depth of the effective concrete area. Okay, so we are going to write an equilibrium as CC plus CS equal to TS. Compression steel, compression concrete, compression steel, and tension steel. So let's write a compression concrete or 0.85 multiplied with FCD. What is FCD? You can see here is the design strength of the concrete, 16.67 multiplied with 300 BW. This is BW, this length from that point to that point, and multiplied with A plus the compression steel. That means that the compression steel area, 628 multiplied with 365.22 equal to the area of the tension steel multiplied with 365.22 also. And from here I'm gonna obtain A is equal to 109.3 millimeter. And C also, we have to find the neutral axis, as I said, K1 multiplies CA. So the K1 is here 0.85 because of the type of the concrete, C25, and the C will be 128.59 millimeter. Now we obtained also neutral axis, and so let's determine that the compression steel has yielded or not. So I'm going to take this epsilon s prime divided this length, and epsilon cu I'm going to divide at this length. Okay, so this is going to be something like that: epsilon s prime over c 128.59 minus, as d prime is the rust cover, 40 equal to 0.003 over 128.59, and due to this equation, this will be equal to 0.0027, and this is greater than normal yield point of steel is equal to 0.001825. So the compression steel has yielded. The assumption is correct, so we are going to go on to solve the question. Okay, we don't need to find any new C value. So let's check it is under reinforced or tension controlled or compression controlled. So for this one, we are going to obtain the yield point of tension steel, and this will be epsilon s over d. What is d? 560 minus C value 128.59 equal to 0.003 over 128.59. Let's show you that how I did. For this epsilon s, I'm going to divide to this length, and for this one, this is also equal to 0.003, yield point of the concrete, and I'm going to divide this length to this length. Okay, so now I did this before I told you, and from this I'm going to obtain as 0.01. This is the yield point of the tension steel. It is much greater than the yield point of the steel. So it is tension controlled, okay? Now the first part is okay, so let's solve the second part. Estimate the balanced steel area, then check the reinforcement steel area is over or under reinforced. So this was the first part and this is the second part. Now I'm going to solve. I want for the second part, for when I find the balanced steel area, I want my reinforcement and the concrete should yield at the same time, okay? The reinforcement and the concrete should yield at the same time. So I'm going to write and compatibility something like this. This is for the yield point of tension steel, okay? Over, I told you that before, this is going to be from that point until that point, this is D. So 560 minus, this is C, okay? But this is going to be C balance. I just give this sketch as to try to teach you. And this will be 0.003. This is for the concrete, okay? I'm going to divide to CB value. And from this compatibility, I'm going to obtain CB as 348.11 millimeter. And if you remember that, I told you that A is equal to K1 multiplied C. And K1 is here 0.85 because the concrete type didn't change. So the AB will be equal to 295.9 millimeter, okay? Now I obtain also AB and CB. So let's write the equilibrium and determine the balanced steel area, okay? So for the equilibrium, CC plus CS equal to tension steel 0.85, this for compression concrete, multiplied with FCD 16.67 and multiply 300 as the BW and multiply with A. What is A? This A I'm gonna use because it's going to be A balance, okay? 295.9 and plus CC. What is CC? CC, the area of the concrete, the compression steel multiplied with the yield strength of the the compression steel and the yield strength of the steel, okay? Compression steel. So sorry, I'm gonna write in here like this. This is going to be equal to tension steel, but the ASB multiplied with 365.22, okay? This equation will be equal to this part. So from here, I'm gonna obtain as balanced steel area will be equal to 4072.02 millimeter square, okay? Now I obtain this, so let's check that it is under reinforced and over reinforced. AS equal to 1900 millimeter square, and it is smaller than ASB is equal to 4072.02 millimeter square. So if it is smaller than the balanced steel area, so that means that the beam is under reinforced, okay? And now we solve the second part. So let's solve the third part. For the third part, we say determine the ratio of steel in the cross section. So let's write them here. The ratio of steel in the cross section. For example, rho. Rho for the tension steel, it's going to be AS over BW multiplied D. Okay. So what is AS? AS is 1900, right? Yeah. And multiplied with 300, multiplied with 560. So this is going to be equal to 0.01113. Okay, so let's determine here rho prime as prime over bw multiply d 628 over 300 multiplied 560, and this will be equal to 0.0037. So let's write the balanced. For the balanced ratio, it's going to be as b over bw multiplied with d. What is ASB? ASB, I determined it before. This is 4072.02 over 300 multiplied with 560. And from this, I'm gonna obtain 0.0242. Okay. So let's determine the rho mean also. For rho mean, it's going to be 0.8 multiplied FCTD over FYD. Okay, and this will be 0.8 multiplied with 1.2 over 365.22. And this will be also equal to 0.0026. So let's write the for rho max. 0.85 multiplied rho b 0.85 multiplied with, what is rho b? Rho b we determine it here, 0.0242, and this will be equal to 0.026. So let's make a check. We're going to make a check. Rho has to be smaller than, rho has to be smaller than, so rho mean 0.0026 smaller than rho minus rho prime and equal to 0.0076. Now you can see it is, so it is okay. And let's make the compression still has yielded. So we're going to make a comparison also there. Rho minus rho prime smaller than rho balanced. So it's going to be 0.0113 minus 0.0037, and this will be equal to 0.0076 smaller than 0.0242. And now it's also okay. So the beam is under reinforced. Now we made our check, so now it's okay. So let's find the fourth part. For the fourth part, it asks to determine the moment. The moment can be carried by our cross section. Okay. Determine MR. What is MR? MR, the moment can be carried by our cross section. So let's find it. The moment will be determined like that. MR will be equal to CC multiplied with D minus A over 2 and plus CS multiplied with D minus D prime. So we are going to take the moment with respect to the tension steel point. Okay, so it's going to be at this point, to that point. Look at here. I'm gonna show you for the first drawing. To that point, compression steel will act at this point, from that point until here. So we're going to just take as D minus D prime, okay, for the compression steel, right? For compression concrete, we are going to take the half of this length because it's going to directly take the midpoint of the effective concrete depth and from the dead point and until the dead point. So it's going to be D minus A over 2, okay? The length, it comes from there actually. So let's write the equation. 0.85 multiplied with FCD 16.67, the design strength of the concrete, multiplied BW and multiply with A. What is A? A is 109.3, okay? And plus parenthesis 560 minus 109 over 0.3 over 2 and plus CS. What is CS? 628 multiplied 365.22 and multiplied with 560 minus 40 rust cover. From this, we are going to obtain as the moment 354.06 kilonewton meter as the moment can be carried by our cross section. Now the MR also be determined. So let's look at the part 5th. At part 5th, check if it is okay or not for the ultimate moment of the beam of given 8 meter length. So that means that the moment can be created by these forces at the 8 meter spans. Now you can see that we can be carried by this our cross section. We are going to make a compare. Okay, so let's make it. Let's solve it here. 5th part. And the first, this is MU, okay? So first we are going to determine the force. This is going to be dead load, and 1.6, this is going to be live load, okay? This is a coefficient of to stay at the safe side. So this is going to be QU equal to 1.4 multiplied with 15 and plus 1.6 multiplied 10 equal to 37 kilonewton meter as the design load, okay? So, and this MU will be determined Q L square over 8, and from here 37 multiplied with 8 square, L is 8. I can show you, maybe we missed, so we're gonna check it again. This is L, you can see it is 8, okay? So, and this will be 8 square and over 8, that will be equal to 296 kilonewton meter as the moment can be created by this force, by this 37 kilonewton meter force that will be created as this moment. So we're going to make a compare. MR is equal to 354.06 kilonewton meter. It is greater than MU is equal to 296 kilonewton meter. So MR is greater than MU. That means that our cross section can carry this moment, can be created, okay? The moment will be created by this design force. So now we're going to write that it is okay. The design is okay now. The moment can be carried. So the question is solved. If you like these videos, if you want to see more of the videos, please subscribe and share with your friends. If I did something wrong, please comment. I'm gonna fix it. See you for the next question.